Good morning, everyone. My name is Rawan Siaj from Palestine Polytechnic University. I will talk about analytic and geometric study of quasi-conformal mapping with application to boundary value problem. This paper under a supervisor, Dr. Ahmed Khamaisi. I will talk about concept of conformality, mathematically and formally. Then I will talk that conformal map take curve to curve, not flat to flat. Then how I reach to quasi-conformal map after conformal mapping. Then some theorems about quasi-conformal mapping. Then I make comparison between quasi-conformal mapping and conformal mapping. Then I will talk about geometric boundary value problem. The word conformal means same form or same shape. Mathematically, it means the invariance of some geometric characteristics. Formally, a conformal map is defined as a function which preserves angles, shapes, lengths, or areas, not all of them in the same function. If we given a holomorphic function, holomorphic meaning conformal mapping, and let lambda equal in norm of the first derivative of chi of z that greater than 0, then the Jacobian matrix of the mapping is equal lambda multiplying by the rotation matrix. Rotation matrix is presented here. Now, I will talk about Riemann mapping theorem. Riemann mapping theorem, it is the easiest way to prove that there is a homomorphism function between two simply connected domain. Every simply connected Riemann surface can be mapped conformally onto the sphere, the plane, or the unit disk, and the resulting mapping is unique up to Mobius transformation. Conformal maps are maps between Riemann surfaces which preserves angles. We say that the transformation chi z is conformal on omega, then the Riemann mapping theorem asserts that the circle from the domain to a circle in the codomain. Here is the property to conformal mapping. If we have a homomorphism function, then this function is conformal if and only if the real valued function are continuously differentiable and satisfy the orthogonality and the uniformity properties. Okay. Here also properties of conformal mapping. If we have two conformal mapping, then the inverse of conformal map is conformal, and the composed of two conformal map also is conformal. Here is a motivation to quasi-conformal mapping. If we have a homomorphism conformal, if we have a homomorphism from domain rectangle R1 with height H1 and length L1 and to the range R2 rectangle with height H2 and length L2, then the affine transformation L chi is conformal if and only if the aspect ratio height over length are equal. If not equal, this is quasi-conformal. The definition of quasi-conformal mapping, see. Chi is quasi-conformal if chi maps homomorphically onto a rectangle region and is a solution to Beltrami equation. Beltrami equation is a coupled system of first order. If chi z conjugate equals 0, this Beltrami equation reduces to Cauchy-Riemann equation, and quasi-conformal map is conformal map. Properties of quasi-conformal mapping, the inverse of quasi-conformal is quasi-conformal, and the composition between conformal and quasi-conformal mapping also quasi-conformal mapping. Another property or theorem to quasi-conformal mapping, if we have a homomorphism function with a vanishing Jacobian, then chi is quasi-conformal if and only if the real valued function are continuously differentiable and satisfying orthogonality and anisotropy properties. Here is some theorems to quasi-conformal mapping is generalization to theorems for conformal mapping. If we look here, if phi z conjugate equals 0, this theorem reduces to theorem for conformal mapping. We make here comparison between conformal and quasi-conformal. The components of conformal map satisfy Riemann equation, but the components of quasi-conformal mapping satisfy the Beltrami equation. There exists unique conformal mapping that takes boundary curves to boundary curves, not vertices to vertices. But there exists a unique quasi-conformal mapping takes boundary and corner vertices to boundary and corner vertices. Also, the component of conformal maps satisfy Laplace equation, but the components of quasi-conformal maps satisfy the Poisson equation. Conformal maps takes infinitesimal circle to infinitesimal circle, but quasi-conformal map take infinitesimal circle to infinitesimal ellipse. Here example about conformal mapping, and here example for quasi-conformal mapping. Every conformal map is quasi-conformal mapping, but converse is not true. This example quasi-conformal mapping, but not conformal mapping, because not satisfy Cauchy-Riemann equation. Here are some theorems that we need to solve boundary value problem. Say that the boundary, orthogonality property and anisotropy property, if satisfying in the boundary, then it is satisfying in the interior. Here some motivation about boundary value problem and boundary condition which we need to solve Poisson equation. This we can solve by finite difference theorem, finite volume theorem, finite element theorem, which we will discuss it inshallah with Dr. Ahmed Hamaisi in the next thesis inshallah.
Thank you. Any question? Thank you. Arab American University. Please take a seat. Please take a seat. Sausan, you have 12 minutes.
Good morning, everybody. My research about solving three-dimensional Volterra integral equation by the reduced differential transform method. I would like to talk about the abstract Volterra integral equation, the three-dimensional Volterra integral equation, three-dimensional reduced differential transform method, how to solve Volterra integral equation by reduced differential transform method. I will discuss an example, then talk about the conclusion. The abstract, we were successfully to extend the two-dimensional Volterra integral equation, two-dimensional reduced differential transform method to three-dimensional case to solve three-dimensional Volterra integral equation. Using the reduced differential transform method RDTM, the exact solution can be obtained after a few number of iterations. Moreover, we can solve linear and non-linear Volterra integral equation by this method. Integral equation has two major kinds, Volterra integral equation and Fed-Holm integral equation. The general form of Volterra integral equation is given by this formula, where u of x is the unknown function, kx of t is the kernel of the integral equation, lambda is constant, 5x and f of x is known function. For 5x equal 1, we get this formula, which is called a second kind Volterra integral equations. In this work, we consider the following nonlinear three-dimensional Volterra integral equation, where the integer, where m is a positive integer, and the function k is the kernel of the integral equation. We consider that must be analytic and separable. This equations, Volterra integral equation, was solved by many methods, such differential transform method. Three-dimensional reduced differential transform method. This definition gives us the idea of RDTM. If we have any analytic function of three variables, then we can find the reduced transform function by finding the kth partial derivative of it. Also, we need the differential inverse reduced transform of capital W sub kx of y is defined by this series by using the reduced transform function. This is sum of reduced differential transform function, which is used to solve ordinary and partial differential equation. Also, we use it to solve Volterra integral equations. By using the previous definition and the previous table, we were successfully to prove some theorem which contains several shapes of Volterra integral equation. This is the first one, and the reduced form of it. This is the second one, which contains inside the integral a multiple of two function. This is theorem 3, which have a multiple outside the integral equation, and this is the division case inside the integral, and also this is the division case outside the integral also. By using this theorem, we solved many examples. One of this example is this example, u equal g plus a triple integral, where g given by this formula, where the exact solution of it is given is equal e to power x plus y plus t. Using the theorem we were prove it, we can convert the Volterra integral equation to the reduced form, to the reduced form of it, and also convert the function g to the reduced form of it. Now take k equal 0, 1, 2, 3, and etc. We can use this value to write the solution as infinite series, which is a Taylor series of the exact solution around the value t. Also, we make a numerical analysis to make sure that this method is effective. This is the solution at some t equal 0.6, where the green is the exact solution and the other is the approximation solution, where the approximation solution converge up to the exact solution. Also, we find the relative error. If we look to this table, we can see that when the iteration increase, the relative error becomes small and small. Also, we sketch it. As we said that when the number of iteration increase, the relative error will decrease. This is one of the figure that we sketch it. This is at xy equal 0.1. Also, we sketch another point. We find that all the figures we sketch is that was identical whenever we take any x and any y, which means that the only value that affected is the value of t, which means that we can take a small t to get a small error. Also, we find the absolute error using RDTM. Why we calculate this error? Because the example we discussed was solved by another method, which is called DTM. We use the value getting from DTM to compare between RDTM and DTM. This is a figure to compare between the error between DTM and RDTM at xyt equal 0.5. As we say that the error getting from RDTM is better than the error getting from DTM. Conclusion, RDTM works when the kernel is analytic and separable. The privilege of the method is the simplicity and the accuracy. It's worth noting that RDTM does not require complex computational work. The RDTM can be easily implemented. The converge of RDTM is rapid and its approximation is accurate. In general, it can be concluded that RDTM is a powerful tool for solving many linear and nonlinear three-dimensional integral equations. Thank you.
Thank you very much. Any question? Wait. Any other question? Thank you very much. we invite Aman Al Jamal from Palestine Polytechnic University. Welcome, please. You have 12 minutes.
My name is Amani Al Jamal. The title of my presentation, Ideals and Boolean Lycée Mirroring, some properties. From Palestine Polytechnic University, Dr. Nuruddin Rabia. My presentation is divided into three sections: Boolean Lycée Mirroring and some property of Boolean Lycée Mirroring and ideas in Boolean Lycée Mirroring. One section, Boolean Lycée Mirroring. Definition: let G be a group, then G is called Boolean group if and only if all elements other than the identity has order 2. From the definition of Boolean group, we can get that every Boolean group is abelian. Another definition, a Boolean Lycée Mirroring is a non-empty set R together with two binary operations, addition and multiplication, such that the following conditions are satisfied. One condition, R under the addition is a Boolean group, R under the multiplication is a semi-group, the left distributive law is hold, i.e. A dot B plus C equal AB plus AC, and the fourth condition, AB dot A plus B plus AB equal AB for all AB in R. Section 2, some properties of Boolean Lycée Mirroring. One properties, a Boolean Lycée Mirroring R may not has the unity. Definition, a Boolean Lycée Mirroring R is said to be a weak commutative if ABC equal ACB for all ABC in R. Another probability definition, a Boolean Lycée Mirroring R is said to be zero symmetric if 0 phi A equals 0 for all A in R. Every Boolean Lycée Mirroring R is a zero symmetric. The writer of scientific paper stated that if in a Boolean Lycée Mirroring R and for any A in R, we get A dot 0 equals 0. And if R is a weak commutative, we get 0 dot A equal to 0. However, we know that every Boolean Lycée Mirroring is a zero symmetric. This implies that in any Boolean Lycée Mirroring R and for any A in R, we get 0 dot A equal A dot 0 and equal 0, even if R is not a weak commutative. Another probability of Boolean Lycée Mirroring, if R is a finite Boolean Lycée Mirroring, then R has 2 to the power k element for some positive integer k, and we can prove this theorem by Cauchy theorem. Another probability or definition, let R and R prime be Boolean Lycée Mirroring. A mapping F from R into R prime is said to be a homomorphism if from R into R prime if the following conditions are satisfied. One condition, F A plus B equal F A plus F B, and F A B equal F A dot F B. A mapping theorem, a mapping F from a Boolean Lycée Mirroring R into a Boolean Lycée Mirroring R prime, then F0 equals 0 prime, and FR is a weak commutative if R is a weak commutative. Section 3, ideas in Boolean Lycée Mirroring. Definition. A non-empty subset I of a Boolean Lycée Mirroring R is said to be any ideal of R if the following conditions are satisfied. One condition, R under the addition is a subgroup of R under the addition, means that for all A, B in I, A plus B is also in I. Condition 2, R A belongs to I for all A in I and R in R, means that the set Ri subset of I. And the third condition, R plus A dot S plus RS belongs to I for all R S in R, and for all A in I. Remark, if R is a weak commutative Boolean Lycemi ring and I is any ideal in I, then AR belongs to I for all A in I and R in R. Another theorem, if I and J are ideals of a Boolean Lycemi ring R, then the intersection intersection J is also an ideal of R. But the union of two ideals of a Boolean Lycemi ring may not necessarily to be ideals. But if one of the ideals is contained in the other, then the union of it is any ideals of a Boolean Lycemi ring. The non-radical ideal, the set of all nilpotent elements of a weak commutative Boolean Lycemi ring form any ideal of R. This ideal is called the non-radical ideal and is denoted by N of R. The contraction ideals theorem, let R and S be Boolean Lycemi ring and let I be any ideals of a Boolean Lycemi ring S, and let F mapping or homomorphism from R to S, then F, the set F inverse of I is any ideal of R. This set F inverse of I is called the contraction of I and is denoted by I contraction. Any I definition, any ideal R not equal to R is called, of a Boolean Lycemi ring R is called a prime ideal if and only if A, B belongs to R, then either A in R or B in R. Another definition, let I and J be ideals of a Boolean Lycemi ring R, then I and J are called co-maximal ideal if I plus J equal to R. Theorem, let F be a homomorphism of a Boolean Lycemi ring R into a Boolean Lycemi ring S, and let a Q is a prime ideal of S, then the contraction ideal of a Q is a prime ideal of R. Mean that the contraction ideal of a prime ideal is also prime. Another theorem, let R be a Boolean Lycemi ring and N be the non-radical ideal, then N is equal to the interaction of all prime ideals of R. The quotient Boolean Lycemi ring. If I is any ideal of a Boolean Lycemi ring R, then the set R module I, it is equal all elements of the form X plus I for X, where X from R is also Boolean Lycemi ring. Boolean Lycemi ring. This Boolean Lycemi ring is called quotient Boolean Lycemi ring. Theorem, let R be a Boolean Lycemi ring and N be the non-radical ideal, then the set R module N has no non-trivial nilpotent element. Maximal ideal, any ideal M of a Boolean Lycemi ring R is maximal if M not equal to R and if there is no ideal I such that M subset of I subset of R. Theorem, let R be a Boolean Lycemi ring and I be a proper ideal of a Boolean Lycemi ring, then there exists a maximal ideal M such that I subset of M, mean that I contained in M. Thanks you.
Thank you very much. Any question?
Onto one, two, homomorphism بس. homomorphism. بتصير اي ما فهمتش عيدها خلي
Repeat.
of f. لا false false أكيد false. لما يكون isomorphism one and
Any question?
example for yes but تعطيك example عشان you need two operations
تقدر تسوي واحد؟
yeah 0 1 set 0 1
Any other question? Thank you very much.
موجود اصلا، هو مش مودي طلب اصلا يعني.
اللي من غزة مش موجود. بريك. لا السيشن خلاص. بريك. ايش اللي من غزة مش جاي؟ لا هذاك سيشن ثاني. سيشن ثاني. بجوز ما يجيش كمان. لونج بريك. هاف ان اور.
بتاع الصفة.
هاي بالضبط.
هذا موجود هي هون. Okay, the first speaker is not available now, so we come back to it after Suha. Our first speaker in this session is Suha Jazzar from Arab American University, and she's gonna talk about what you see.
Hello everybody. Today I'll talk about derivation and simulation of eliminated multivariable range Hopin parameters. Here our outlines, introduction, simulation, result and discussion and conclusion. Okay. In our introduction, what is Hopin conduction? It is electrons hopping or transport from one localized state to another. And there are three types of Hopin conduction, which are thermally assisted tunneling process with the emission of phonons. And there are three necessary conditions to occurrence the Hopin, which are wave function of the two localized states must overlap. Second one, occupied and empty states must present to the Hopin to occur. And two, hopping from one localized state to another with a higher energy needs energy. What is VRH, variable range hopping? It is a model that describing the low temperature conduction and strongly disordered system with localized charge carrier states. And it is a very important model because it is described for many conduction effect on the many devices, for example, random access memory RAM devices, and have shown that the accumulative of metallic ions shortens the Hopin range and decreases the activation energy. And due to their important applications in photonic technology designs, there are this crystal, which is thallium, silver, selenium, which is type of Ramsey crystal system, captured by attention of the researchers, and it is conducted by Hopin conduction. In our work, we obtained an experimental data and given the conduction mechanism of our crystal, and we have the interval of temperature between 320 up to 150 Kelvin. And we have observed the effect of the Hopin parameters on this crystal under photoexcitation and in the dark, and we have distinct light intensity from 50, 55, 60 up to 80 milliwatt per centimeters square. Here we have Mott's theory in 1969, and this formula put by Mott's, and here T node is the degree of disorder and given by the next relation, and we have other important parameters of Mott's, which are N of EF, density of a state near Fermi level, and Hopin distance R and Hopin energy W, given by the other relation respectively. In our simulation, we sketch this figure, and here we can observe the effect of the electrical conductivity that's increasing with increasing of light intensity F. So it is the photoexcitation effect on the Mott's variable equation. So we have to recalculate the parameters of Mott's variable range Hopin parameters, and we using the dimension D equal 3. Here we sketch the linear variation of length sigma versus T to the power minus 1/4. And from this sketch, we can reflect the validity of the Hopin transport in the dark and under photoexcitation. So we can determine T node, degree of disorder, from the slope, from this sketch. What about T node? T node is decreasing, as we show in this figure, decreasing with increasing in light intensity. And we have gap from dark and light intensity. Here, other parameters. First one, N of E Fermi, increasing with decreasing in light intensity. So it is not constant. And from the other sketch, W and R respectively, they are decreasing with increasing in light intensity. Okay, what is the result from our simulation? The main result, which are, as the thermal equilibrium condition is now disturbed by the light and the heat. So the net charge carrier density couldn't remain constant. So we want to, or we have to reconsider the validity of mass variable range hopping equation under the assumption of non-constant. Okay, here, in 2009, Butesh gave full mathematical analytical analysis to the model that assumed the polynomial density of a state in this form, N of E equal N of E Fermi plus SQ multiplied by E. And he puts two necessary conditions, which are each conductive must be at least equal to the critical conductivity, sigma Ig, more than or equal sigma C. The other one, the average number of conductance linked to each site located at energy Ej must be equal at least to the critical concentration C. So C equal the average number of M of EI. And to evaluate M of EI, it is necessary to count all sites located at energy Ej accessible by the electron located at the site EI. Such Ej sites are randomly distributed in the sphere with radius Rij. So MEI equal the integral of the volume of the sphere multiplied by density of state dEj. To find Rij, we back to the first condition and find by the inequality Eij and both the equality to find the value of Rij. We substitute the value of Rij and N of E Fermi at all possible situations besides the possible values for Eij with all limits. So we have this formula of M of EI. Then we integrate by parts, and we get the second formula. And Butesh assumed that M of E have two functions, one dependent on a Q, and the other one, M0 of EI, is independent of a Q, which is a Q is odd number, where it have the, respectively, these formulas. Okay, then we concerns the number, the average number C, and we get C equal this formula. And then we substitute N of EF and M of EI and neglect the asymmetry items. And then we reach to this relation, C equal this relation. And then we know that C is a constant number, equal 1.5. When we substitute T value, T node value, and C, we get this beautiful relation, which is mean that the assumed density of a state is still valid by Mott's equation. Okay, the experimental density of a state. This is our assumption. We assume that the density of a state has this relation with N of E equal N node exponential E minus EF over E node. And then we take the same technique of Butesh. And we take also the same assumptions. Then we obtain, after many mathematics calculation, we obtain this formula of M of X and density of a state exponential. And then we find the average number of length, and we account that the exponential density of a state equals this formula. And then we can write C see as the following formula. After many calculations, we get this huge formula. It's clear that it is a very complicated formula. Then, from the expression, it is very difficult to find C analytically. So we go to the numerically way to prove that the validity of the Hoping energy EM with this relation in exponential density of state. And after we go to the numerical, we compare between the polynomial, which is assumed it's valid, and we prove that, and we compare between the two curves in exponential density of state and polynomial density of state, and from the best correlation, we can find EM. And here, if we observe that the interval of our research from 150 up to 320 have matched in the two curves. And so we prove the validity of density of state and exponential assumption or formula. Our conclusion, the photoexcitation, of course, it is effect on Mott's variable range Hoping. So the Hoping transport is easily controlled by photoexcitation. And photoexcitation can reduce the Hoping energy. The electron can move to wider distance via photoexcitation. And the higher the light intensity, the less the degree of disorder, the low heat and energy consumption. And even though Mott derived his theory assuming constant density of a state, localized state, it is still correct for variable, polynomial, and exponential density of a state when extra light energy is supplied to moving the electrons. Thank you.
Okay, we thank the speaker again. I think we move to the next one before we go back to the guy from Gaza. Because according to the schedule, he's supposed to talk at 10:40. So maybe he's not online. Maybe he will be online at 10:40. So we go to the next one, and then we go back to the guy in Al-Azhar. So we move to the next speaker, Marwa Shihada from Palestine Polytechnic University, and she's going to talk about adaptive finite difference scale for the wave equation.
Thank you. Welcome everybody. Welcome everybody. I am Marwa Shihada from Palestine Polytechnic University. I will talk now about adaptive finite difference scheme for the wave equation. My supervisor is Dr. Ahmed Khamaisa. Okay, let's start talking about adaptivity. Adaptive methods in computational fluid dynamics have received much attention in past 30 years. For physical and engineering area, adaptive methods play an important role in computational applications such as solid, fluid dynamics, and heat transfer, and etc. So, what is adaptive method? Adaptive method or adaptive mesh refinement refers to the modification of an existing point to capture more accurate solution. So, what is the aim? What is the aim for adaptivity? Is improve and capture the accuracy of the solution, minimize the computational cost of the solution, and reduce the computational error of the solution. And finally, produce a more accurate solution when compared with uniform mesh solution. Okay, so let's talk about the equation, one-way wave equation, ut plus aux equals 0, where our adaptive method is talking about. So, with this initial condition, sorry. This is the initial condition, and this is the boundary condition, and this is the exact condition obtained by using characteristic method. I will talk firstly about the explicit and implicit schemes I use in my method. The explicit method is upwind scheme, Lax-Friedrich scheme, Lax-Windorf scheme, where the implicit scheme I use Craig-Nicholson. So, let's take about, and we'll talk about the mathematical tools, that's convergency, consistency, order of accuracy, and the stability, where I proved it for the previous explicit and implicit scheme I presented. So it's a proof. For stability, I use CFL condition, Courant, Friedrich, Lowy condition to prove the stability, and von Neumann analysis to prove the other stability. Okay. The stability for the explicit and implicit schemes. Let's start about the important things in my work. It's about adaptive method strategy. We have two strategies here, H adaptivity and R adaptivity. My work is talking about R adaptivity or mesh motion, but I will talk firstly about H adaptivity to see the comparison from it between them. Okay, R adaptivity or element subdivision, it's talking or based on inserting and removing points with final goal of resolving the local physical length scale. Where the disadvantages for this method that the subdivision alone may be caused in abrupt or non-smooth transition along the solution. Where our adaptivity, where my work based on, is talking or allowing the concentration of points in area of high curvature or large error to capture or without using an excessive number of points with the final goal of having the more accurate solution. So let's talk about firstly about the physical mathematical setting I used in my work. This is the physical solution. And the technique of the discretization process I used is depend on mapping from computational zeta domain to spatial domain x to having the composite mapping x zeta, zeta from 0 to m. Then the composite mapping x zeta having properties where the mesh point should be closely spaced in the area where a large error expected. Number two, where the angular deviation of mesh edges should vary smoothly along the solution. So we'll talk about hyperpoint distribution strategy for adaptivity, where it's very important, where it's a strategy for the process of adaptive meshing, allowing point distribution to be focused on parameter measures, arc length, curvature, error, alone or union to achieve a suitable mesh discretization, resulting in a more accurate numerical solution. Okay, there is some of physical consideration for hybrid approach. We should talk about for the density function rho, where it's the equal arc length spacing, where points are separated by equal distance along the solution, where the density function is proportional to arc length, where it's not visible here, where and error-weighted arc length spacing, where the point concentrated or clustered in the area of high error, and finally the curvature-weighted arc length spacing, where points separated in area of large curvature. So we have the density function, which is the linear combination of the above characteristic, where the lambdas, the summation of it equal 1. Okay, now let's start about the first method of adaptivity called variational adaptivity method. And I will talk it about fastly because it's a common method, where the important method in my work is that the second one, which is called direct adaptivity. Variational mesh adaptivity, it's based on minimizing the weighted gradient arc length of the mesh element. It's talk about the minimizing the energy functional Fs. Then we have to use node mobility function with the linear combination, as you see here. We use the Euler-Lagrange variational equation, and its solution is the solution for the energy functional above. Okay, by using some calculation, we get this elliptic adaptive system with this boundary condition to get finally to this couple system from the wave equation together with the mesh equation that give me the adaptive solution. But this method have to do a lot of iteration, and that's make a computational cost. So we have to research for another methods that cost me a less cost in computation. So we go to direct mesh adaptivity mesh for it's a modified approach for the adaptive mesh to obtaining a more faithful numerical solution to the wave equation. The essence of this method is to directly compute zeta x, and by integrating the density function over the solution domain, then getting the inverse transformation to get x zeta. We don't have iteration here. So we have to consider the density function as previously. This is the weight length, the weights. This is the inverse transformation or formulation. This is the normalization we use in our computations. But I will talk here a simple note where the hyperdensity function will migrate mesh points into region where any one of the function ρ I mandate refinement. Okay, so let us, this is the coupled system. This is the coupled integral differential equation from the wave equation ut plus aux with the mesh equation x zeta. And by solving this system, we get the best and the closest solution to the exact solution. Okay, the closest numerical, of course, solution to the exact solution. So this is some consideration we used, where the mesh density function for our legs is given by this formula, and for the curvature, for error and for the curvature. So by all these computations, we get the adaptive method. The final section or the final things I want to say is the practical things I get from this work, where there is the numerical results and analysis. So first case, I used a point scheme for wave equation. I take the wave speed A equal 1 for x between -3 and 3 and t between 0 and 1. For this initial and this boundary, this initial condition, we have the exact solution here. I will say a note. My cases all have exact solution. So can I compare with the numerical and adaptivity, and uniform and adaptivity. So I get the error L2 norm and L infinity norm error to compare between the results, we can see that in uniform in the uniform L2 uniform and L infinity uniform 1.4 etc. And for adaptivity 0.03318 and etc. and for L infinity 0.05418, we can see and notice that the error is so smaller when compared with the uniform, and that's what we want. So let's see the graph here. The green one is the uniform, the green line is the uniform solution, the red one is the adaptive, the black one is the exact. All body here can notice that the red line is the adaptive. This is my method. It's so closely to the exact solution. We can see that also that the points here are concentrated in the area of error or high error. Here we have high error in uniform. Here in uniform we have high error, and we have a high curvature points clustered in this area and capture this error and correct it, so we have the best numerical solution closely to the exact one. This is another one. Can see that another graph that we can see that the adaptive method is so closely to exact solution. Okay, the second case, firstly, is also a wave equation. This is the exact solution. This is the initial condition. So we have also, by using the error, by comparing the error, we can see that the error is so close, so smaller when compared with the uniform one. So in the chart, also we can see here that the points separated or clustered in area of high error and in high curvature and fixed the solution to be very near to the exact solution, and that's what we want. And we will note that the adaptive solution can capture the discontinuity in the solution and fix it, but uniform can't do that. Okay, this is the graph. Also, the third case is by using Lax-Windorf scheme. Also, we can see when comparing the norm error. The norm, that the error is very smaller when compared with uniform for adaptivity. And also for the graph here, where points are clustered in the area of large error and capture it by using the adaptive, the green one is very close to the black line, that's the exact. And that's the goal here. Okay, the final one is by using Crack-Nicholson for implicit scheme. We also can just by using by seeing or showing the results that the error is so smaller, and that's what we want. So this is the graph that tells us what happened here. The points clustered in the area of large error and large curvature, capture it and fix it and get and obtain the best numerical solution we can get when compared with the exact solution. Thank you for your attention. Thank you. Thank you. Okay. And variational method. Okay. Okay. In variation method, okay. Okay. Euler, here. Okay. Okay. we have here an elliptic adaptive equation, m s zeta zeta plus mu zeta s zeta equals 0. This is the adaptive equation here. The adaptive equation. Okay. Okay. Another question? In the first, let me go start. Where? Here? Here? In H adaptivity. In H adaptivity, right? And maybe in H adaptivity when I said that it's not if you mean for H adaptivity, that's the smooth. What is mean non-smoothly here, right? When we insert and removing points, maybe the points can cluster closely to each other, so that that will result in a gap between the other points. Can you understand me? Yeah, that's what we mean non-smoothly. Yeah. We do that in direct. We do that in direct method. Yeah. Yes. Another question? In test cases, you mean? Yes. What about the boundary? Repeat again. I don't hear all the question. Okay. Okay. Okay.
You have a finite length. Boundary.
Okay. Yes.
Okay.
I mentioned that in my work. I mentioned that. Maybe I don't talk about in. I don't mention it in presentation. But in the first wave equation, I talk about 1 second. Here, yeah. This is the boundary condition I used in my work. In each case, I put my boundary condition. Yeah.
No. Wait. You mean you have a semi-infinite line?
No.
No.
We don't have
semi-infinite.
semi-infinite.
Here, x equals 0. You have a constraint in x equal to 0 and r x greater than 0. There's a semi-infinite line. Okay. And you say that you have tried in finite length with boundary condition, Dirichlet or Neumann, and it's worked very well.
Let me go to the case to show you that, for example, for the first case in upwind scheme, I initialize x between -3 and 3 and t between 0 and 1. Okay.
What else is the boundary condition in -3 and 3?
Yeah. We used, but I don't mention it in presentation because it's yeah. But we do. Of course, we mentioned that. We use that.
Dirichlet or Neumann? You did it.
What?
Dirichlet or Neumann condition? Dirichlet. Yeah.
We used extrapolation and interpolation boundary. Okay.
Okay. Dirichlet.
Okay.
But during the
Yes. First or the next? Next. انا مش كاتبته على فكره مش ما عملناهوش على البرزنتيشن احنا. ارجع.
Thank you. You have a nice talk.
The left boundary and Dr. Ahmad. The left boundary, Dr. Idris, and the right boundary in the initial step, we fixed it, okay? And then we take an discretization process, and we used iteratively the points inside in extrapolation and interpolation boundaries. I think that if you, okay. Okay. Okay, okay. Okay, okay, okay. This is the couple system of direct, Dr. Ahmad. Yes, this is the couple system of direct we used in our work. Okay. Thank you.
Okay, we try to contact the person in Gaza. So just few minutes. Is the next speaker here? The next speaker, Abdel Fattah Mahmoud. Your talk is here. Oh, okay. I think we are about to start our. Okay, the next speaker will be Abdullah, Abdel Fattah, Hosni Mahmoud, Muhammad from Arab American University, and he's going to talk about unified solution for the transport mechanism and equation of electronic conduction.
Unified solution for the transport mechanisms of equations of electronic conduction. This project supervised by Professor Dr. Atif Qasrawi and Abdul Halim Zaiqan, and we published a paper in scientific journal. Due to the vital role of the electronic transport on the performance of electronic devices, conduction mechanism of charge carriers has been attracting the interest of researchers for its importance in solid materials. The investigation of the current transport determines the device operation mode, particularly poorly conducting solids used in passive device application like complementary metal oxide semiconductor. On the other hand, moderately conductive materials used in dynamical device applications like absorption, fast diodes and others electronic devices. The current conduction mechanism has directed the attention of mathematical researchers for its importance, and they found the dominant mechanism at specific range of temperatures, where thermionic emission mechanism dominate at high range of temperatures and thermally assisted tunneling dominate at the middle range of temperatures. And Hoping mechanism or Moore's variable dominant mechanism, Moore's variable range Hoping mechanism dominate at low temperatures. The conductivity as a function of temperature is analyzing according to three different mechanisms. The first mechanism, which dominates at high temperature, is thermionic emission mechanism. And the parameters, sigma 0 is the exponential factor, and E tau the activation energy. K here is Boltzmann constant. مش واضحة. Maybe. Yes. Sigma 0 is the exponential factor, and E tau is the activation energy. K Boltzmann constant, and T is temperature always here. The second mechanism, which dominant at the middle range of temperature, is thermally assisted tunneling. Sigma 1 and F are constant. The third, Moore's variable range Hoping or Hoping mechanism, which dominant at low range of temperatures. A0 is the high temperature limit coefficient of conductivity. T0 characteristic temperature coefficient. And the other two Hoping parameters are and W, the Hoping distance and the average Hoping energy. Simulation of dominant regions. In attempt to investigate the problem of mixed conduction mechanism, the problem of mixed conduction mechanism, the solution of the problem is to combine two mechanisms, the Hoping mechanism and thermionic emission mechanism, as a mixed conduction mechanism, because researchers found the mechanisms at specific range, and we want to find the general view of electrical conductivity for all temperatures. In attempt to investigate the problem, we try to figure out the consistency between experimental data and simulated data of electrical conductivity in TL4S3 crystal. Therefore, we plot the natural logarithm of conductivity versus 1000 over T for both experimental and simulated data, and the consistency between the two curves occurred at high range of temperatures. But there is no consistency at the middle range of temperatures. By changing the activation energy, we get another solution where the consistency between the two curves occurred at the middle range of temperatures. So these results are confusing as they indicate two possible solutions in short range of temperatures. Thus, a deeper look for temperature dependence of activation energy is needed, because as we change the activation energy, we get another solution. There are three distinct regions here. This photograph shows the differential activation energy. there are three distinct regions: a region of sloping activation energy below 155 Kelvin, and a region of constant activation energy above 250 Kelvin. And at the middle range of temperature, variable activation energy. The sharp fluctuation near 250 Kelvin is very strange. It indicates either the non-validity of thermodynamic emission equation or the activation energy value is function of some parameter. One assumption is based on literature data is the existence of more than one conduction mechanism at that region. We suggested these three regions are related to three different mechanisms, where mixed conduction coming from the contribution of each dominant mechanism. The general view of electrical conductivity as a function of temperature is decreasing as the temperature decreases. To find the parameters, the activation energies related to three different regions, traditionally we fit the curves by straight lines within different regions of temperatures. In fact, the activation energies and pre-exponential factors are the slopes and vertical intercepts respectively for the fitting lines. For that purpose, we designed a simulator program, the first page of simulator for that purpose, and the first step is to enter the Excel file location and then plot the general view of electrical conductivity here. The second step is to enter the ranges of dominant mechanisms and then push approximation buttons respectively to get the parameters in the edit text above, activation energies and pre-exponential factors, and the edit text above the approximation buttons indicate how much the fitting is good. The upper part here, the lower part of the page is due to hopping mechanism, and to find the hopping parameters at specific temperature, we is fitting by linear approximation the conductivity at low temperature. We can save this parameter among the program because we use it in the future. Simulation of mixed conduction mechanism. We have two solutions to the problem. The first solution is thermodynamic conductivity, which is a linear combination of the thermodynamic equations, and we can write it as sigma 1 multiply as a common factor multiplied by exponential of g of x, where g of x is a natural logarithm for 1 plus x, and x is the contribution from the second and third conductivity to the first one. The second solution is total conductivity, which is an improvement solution to the first one by adding additional term, which is the Hobbing mechanism, which is dominant at low temperature. The additional assumption for both solutions is to expand the terms g of x and h of x respectively. The value of contribution x can be approximated by these values: exponential of g of x minus 1 and exponential of h of x minus 1. This diagram shows the simulated data of the first solution, thermodynamic conductivity, simulated the experimental data. All simulated data, sigma 1 exponential of g of x, sharply increasing at some parameter. And the consistency between experimental data and simulated data occurred only at high temperatures above 250 Kelvin. But when we use critical parameters to evaluate the critical point, when we use critical parameters or temperature less than 250 Kelvin, the distance between the two curves increased. The contribution of the second and third conductivity according to the first solution is increasing as the temperature decreases. And this means that the value of g of x increased. And this is the reason why the divergence between experimental data and simulated data in the previous figure. When we assume the thermodynamic conductivity, the first solution simulated the experimental data without Taylor approximation, we have a good approximation at all temperatures except at low temperatures. And by assuming a Hobbing mechanism which dominant low temperature at low temperatures, we get a good approximation at low temperatures only. And by combination of these mechanisms, the total conductivity give us a good approximation for all temperature without Taylor approximation. This figure shows the contribution from the first solution to the second solution and justify the mixed conduction mechanism at the middle range of temperature. And also, the Hobin mechanism approaches to zero at high range of temperatures, and the thermodynamic mechanisms approaches to zero at low temperatures. Among the simulator, we extend our assumption to assume all parameters are function of temperatures in linear and quadratic cases. And this figure shows the total conductivity simulated experimental data when all parameters are linear function of temperatures. So we reduce the erroneous estimations when we use parameters as linear functions of temperature. And this is the corresponding contribution of the all conductivities to the first one according to the total conductivity. Here are the total conductivity or mixed conduction simulated experimental data without Taylor approximation. So we have a good approximation for all temperature. Now here I'm talking about conduction contribution without Taylor approximation, an attempt to clarify the proposed idea of mixed conduction as a composed of thermodynamic and Hobin mechanism is the most probable idea, is the most probable mechanism for all temperatures. We found the contribution from each dominant mechanism to the total conductivity in the presence of mixed conduction mechanism. And the first conductivity sigma 1 exists but terminates at 130 Kelvin. And the second conductivity dominant weakly but terminates on 90 Kelvin. And sigma 3 dominates for all temperatures below 250 Kelvin. The Hobin mechanism dominates for all temperatures and be relatively stronger at low temperatures. Inside the dashed circle, the conductivity is shared equally. And if we assume the third activation energy is zero, means that the third conductivity does not exist. The Hobin mechanism dominates even at 300 Kelvin and be strong and increasing continuously at low temperatures. This figure shows the fitting of differential activation energy of experimental data by differential activation energy of total conductivity with E3 is equal 0 and without. And this table shows the evaluated electrical parameter for Cu TL4S3 EC crystal and CuAlO2 thin films in the presence of experimental data and in the presence of mixed conduction mechanism. So the mixed conduction mechanism always exists. And the new approach correct the evaluated electrical parameters. And the proposed model also used to explain the mechanisms of dominant mechanisms and investigate their parameters in TL4S3 EC crystal and in CuAlO2 thin films. Thank you. Yes. No worry. Yes.
How do you measure conductivity?
Experimental data by laboratory. But I work with Professor Dr. Atif Qasrawi from physics department, and he gave me the experimental data of electrical conductivity. Yes, we published the paper. This crystal discovered by Turkish scientists. Thank you.
Okay, I think we're gonna. Okay, there is one announcement. If the invited speaker did not show up, we will finish exactly at 11:30. and he just told me at 11:30 we're gonna go to the other building for closing. 11:30. What is it? 11 now, I think. Yeah, we have 2 more talks then. So we finish at 11:30 and then we move to the other building for the closing. Sorry? The first one is not here. Let's see this. Now we are Areen. Is Areen here? She's not here. Okay, what about the next one? Nadeem. Nadeem? From Pakistan, yeah, so he's not here. Okay, so these two, so let me try, we should try to contact the first one, the invited, if you don't mind. We still have time. Maybe he's online now. No, the first speaker, Marwan, is not here. I think Marwan is still not here. Do you see him? No, he's not here. Okay, so that's it for this session. We meet at 11:30 in the business building, I believe. Yeah. The Areen is coming. She is in the road. She needs 5-10 minutes. Shall we wait or? Okay. Okay, excuse me. I mean, here talk's supposed to be at 11:15.
And she didn't know that.
And yeah, maybe we should wait for her. We wait 5 minutes, 5 to 10 minutes. So we listen to Areen and then we go to the closing. Okay. said she will not be able to make it. So we finish from here. We go to the closing. Yeah.
جاهز.
Okay, welcome again. We will start our closing ceremony by a few words from the chairman of the conference, Dr. Adli Saleh. Welcome, Dr. Adli.
بسم الله الرحمن الرحيم والصلاة والسلام على أشرف الأنبياء والمرسلين محمد وعلى آله وصحبه أجمعين. It has been a pleasure to have all of you here. This is a less formal closing ceremony. It will be less formal than the opening ceremony. I would like to welcome you again. Even though I know you will be leaving in a few hours, I would like to welcome you again. And I truly look forward to the coming 6th conference that will be held at our sister university, Khaduri. We tried our best to do what we can to provide with the limited infrastructure that we have, with all the limitations that we have on checkpoints, accessibility to the university. We try to do our best. Please forgive us for any shortcomings that you've seen during the conference. Please also be generous with your comments. I will be awaiting for any comments, negative or positive, at my email. I welcome you again, and I wish you a safe trip back home. Thank you, and we will have, of course, we will have lunch, closing lunch right after the ceremony, and we have certificates to give all the participants who contributed a paper or a presentation or a poster. Thank you.
To make this happen. I would like to again thank the organizers who worked so hard to make this happen. Thank you so much.
It's almost over, but not yet. This is the fifth conference, and I hope we will have many, many to come when we are all still healthy and productive. I would like, in the name of everybody as well, especially the people who pay contributions, especially lots and lots of local young people. This was one of the purposes of having these conferences again and again, because we would like to see the new generation involved in research, listening to international speakers, as well as contributing back into the whole scientific program and the whole scientific project. So therefore, I would like to really express my satisfaction with the results of what we achieved. I would like to see more and more high-level research, but then we have to go slowly. We first learn how to crawl, then to walk, and maybe then to run. But meanwhile, we are beyond crawling. So therefore, this is very positive. And I don't want to be very lengthy. I would like to thank everybody, the young, the visitors from abroad, the local organizers, the university, and whoever contributed, because these conferences do not come for free. Lunch does not come. There's no free lunch. Somebody must have put some money into that. We'd like to thank the donors. You didn't mention any donors. I don't know if there's any donors, but no matter what, if there are any donors, we would like to thank them for the contribution, because coming up with resources is not an easy mission. The university, that's fine. Well, we thank the university and whoever is in charge of the university, because I know there are some people in the university contributing. Thank you again, and I wish you a safe trip back home, all of us, and also would like to thank individually every person involved, from the janitors all the way up to the president of the university. So everybody contributed to the success of the conference. Thank you very, very much.
Thanks a lot, Dr. Idris. Anyone want to add any words? John? Okay. Can you come over here?
Well, since this is the, I guess this is supposed to be the feel-good moment. Keep it close to my mouth. Okay, is that better? Is that I'm almost eating it. All right. I wanted to. I'm speaking here now for the foreigners, the people that came here to participate in this meeting, and also, since I was here for the school, I thought it might be worthwhile mentioning something that I mentioned at the school, but I did not put in my presentation. At the end, I have a slide which shows about 20-odd people that I have worked with over the course of my career. And what I mention is, or what is obvious when you see the slide, is that these people are of all shapes, colors, genders, historical backgrounds, cultures, languages, from all over the world. And the point that I like to make at the end of a talk usually is that the reason that it's this way is because physics is so universal. And it is, I think it appeals to, there's something about the universality of physics that appeals to human nature, no matter what your background is, no matter what your history is, no matter what your culture is, no matter what your customs are. Physics, one responds to physics. And I think that the natural interest and stimulation of this discipline is something where we can make a real contribution. We can't do much about politics, but what we can do is invite you, induce you, seduce you, help you participate in this ongoing human and high calling that has been part of humanity's history for such a long time and will continue to be for a long time to come. So that's really all I wanted to say, and I think that I hope I'm speaking for the other people from abroad, from Europe and from the United States, when I say that I think this is really the fundamental part of our motivation, is this invitation to reach you on common ground through physics. Thank you very much. And mathematics. Oh, I'm sorry, mathematics.
Thank you, John. Now with the certificates, so we will be calling your name. So please come down, pick your certificate, and on the way back to your seat, pick a poster. You will be handed a poster. Dr. Iyad will be calling the names.
وعد عواد، ريهام كميل، أماني الجمال، محمد صالح، فريد الغزاوني، سهى جزار، ياسمين غنام، فلاح عواد، نور الدين ربيع، نصوح الصوص، خولة قمحية، حازم أبو سارة، علي أبو زيد، عبد القادر مصطفى، زين فارس، جمال حلوان، فتحي علام، خالد صلاح، جلال درويش، عثمان سليم، أحمد إقبال، محمد كفيل، تمارا عابد، أسامة أبو الركن، وائل كراعين، محمد أبو سمرة، أحمد عمر، علي زين. مرام طالب. يوسف زحايكة. صار الزلوم. عبد الرحيم موسى. رباب جرار، محمد السعيد، سوسن عرميطي، هديل أبو الروب، عنان حسين، إثقال ضراغمي، عبد الرحمن أبو لبدي، عصام عبد الرازق، حنان الطوس، اشتياق حجاز، ألفة عمرية، سليمان رباع، وإيضا أبو صاح، صوان، مروة شحاتي، زيد قمحية، عبد الله الحكواتي، دكتور عدلي صالح، دين وفاكولتي اوف ساينسز، سفيان شحادي، مختار صلاح، هاني قباجة، محمد عدم، سامي السابع، حازم خنفر، عاهد الزيود. محمد أبو جعفر. قتيبة الكرم.
Anybody? But if we did, we apologize. We can actually make one. So after the I'd like to call on two people to come and get their certificates. Dr. Nasser Kamhiye and Dr. Marwan El-Koni. Announcements. Please, one thing, please feel free to take posters if you have colleagues that you need to give them. If you are interested in submitting your manuscript for publication, please make sure to sign the copyright form that I have here. There are copyright forms. Lunch will be in the usual place, and we can actually start walking towards lunch area now. ناصر مين؟ يعني انت احنا بنعطيها بعدين لانه احنا طلع احنا مشكله عملنا شهادات للناس اللي مسجلين فهذا يعني راح يعطيها لانه ناصر سجل باخر لحظه وحيضه يعني راح يعطيها